would like to say to begin with that I really have to thank the organizers for giving me the occasion to talk in person finally after a long time and present my results. So I'm very glad to be here. The title of my talk is Learning to Measure. I will talk about something which I think it's rather general, that is approaches to measurements in n-qubit system or many-body quantum systems. The people that worked with me to obtain these results are my postdocs, Guillermo, Matteo, and Boris. Matteo is here in this conference, and he will give a poster on Wednesday, tomorrow. So it will be about applications of what I'm talking about specifically to quantum chemistry. And this work has been obtained in collaboration with a group of Ivano Tavernelli at IBM Zurich. So the general framework of this talk is the following. You have an n-qubit systems, and then you have some evolution, information processing, some gates. It may be non-unitary, there may be noise. And in the end, you perform some measurements, so you have classical bits, a register of classical bits. It's rather general, and the problem is the following. Say you are given an n-qubit systems prepared in an unknown quantum state. You also are allowed to perform arbitrary but local measurements on the qubits. But you have to choose your measurement strategy in a way blindly. So you don't know beforehand what is the observable, or alternatively, you can think of the need of measuring different observables from the same data set. Okay? So what you may think is that, well, if these are the general conditions, actually the only thing I can do is to tomographically reconstruct the quantum state and then calculate the expectation value, the mean value of the observable or the different observables. And we all know that this is hard. So very often in many problems related to near-term quantum computing or related to experimental conditions, we can't reach this efficiently. So this talk will be about a way to bypass quantum state tomography, which leads to obviously an exponential improvement in the needed resources. It's a new perspective on measurements. So in this sense, we believe is rather general. And the paper is in the archive, and this is the reference. Now, this is my best effort that I made, my drawing, to try to stimulate the experimentalists in the audience, even if I'm a theoretical physicist, to listen, because I think that it might be indeed interesting. So in math, what is the problem we are discussing here about? Let's see if this, sorry, I want to see if the, here it is, yes. So we have a given observable of a many qubit systems, and I write it in terms of so-called Pauli strings. These Pauli strings are just products of Pauli operators. N is the number of qubits, right? So the mean value of this observable is just the sum of the so-called Pauli streams of all these products. And in general, the number, so how large is this sum? How many terms there are in this sum? For many interesting systems, for example, for calculating electronic structures, for quantum chemistry calculations, the terms in the sum are of the order n to the 4, sometimes n to the cube, but they are very many. And of course, this is a problem because if you want to consider the error in the estimation of this mean value, you immediately will see that this is given by the square root of the weighted sum of the variances of all the Pauli strings, divided, of course, by the number of shots to estimate this term. So you have to repeat the measurements very, very, very many times. And in fact, the larger is the number of terms in the sum, the larger is the number of measurement shots that you will need to perform in order to reach statistical accuracy. Okay? And notice that here, this term here can depend on each of the Pauli strings. You may need, depending on the specific Pauli string, different number of measurement repetitions. So generally, this is a problem. And this is no novelty. There have been a lot of different studies to try to overcome this issue. And there are studies for so-called grouped Pauli method. Instead of measuring all the Pauli strings, you can group them and identify those that can be measured from the same data set. You can use classical machine learning, of course, to perform approximate tomography. And there is recently, there have been methods related to so-called classical shadows of a quantum state, which also allow somehow to extract information without doing the full state tomography reconstruction. There are many others. So how our approach differs or compares with this. This is the outline of the talk. I will begin by giving you a little bit of background on the type of measurements we are using, informationally complete generalized measurements. And then the results are in three parts. The first part is the use of a hybrid quantum classical Monte Carlo sampling approach, okay? Then I will see how we can use an adaptive measurement strategy, so to change the measurements in order to go towards the best one, given a certain observable. And finally, I will show how actually you can use the same measurement data set to calculate different observables, different mean values of observables. Now, informationally complete POVM, in particular, remember, I say that I'm going to do local measurements. I'm interested in single qubit POVMs to begin this. So these are mathematically defined in this way. So they are four linearly independent positive operators that I indicate with pi I, the sign to identity, and most importantly, they are basic. They span the entire space of linear operators for the qubits. Okay. In the future, I will indicate with pi I the probability of obtaining outcome I after the generalized measurement pi I. But now, again, you may think, how can I actually implement them in an experiment? How do I implement these operators? In order to do this, you would need actually not one, but two qubits. So there is a little bit of overhead in this implementation. And the way of implementing it is in terms of a general unitary. I parameterize it with the, it's not general actually, it has to have a certain parameterization to realize informationally complete POVM, but it's a unitary that acts on the state of the qubit and an ancilla. And then, of course, the measurement here is the computational basis, and I will associate 0, 0 with the measurement pi naught, 0, 1 with pi 1, 1, 0 to pi 2, 1, 1 with pi 3. Okay, so this is the way in which these are implemented. Okay, so again, in this framework that I presented before, this measurement is now implemented in this way. So I have to have, in this case, not 6, but 12 qubits to implement it. And what I obtain at the end of the measurements are certain strings, 0, 3, 1, 2, blah, 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 because of course I'm repeating the measurements many times to accumulate statistics, and I call M1 the first string of results, M2 the second, M3 the third, and so on and so forth. So I have these collections of measurement outcomes. Now, how does the hybrid quantum classical Monte Carlo sampling works? In order to understand how this is somehow thought, let me rewrite the observable in terms, here I'm writing explicitly the Pauli strings, okay, the products of the Pauli operators. Now, because the measurements are informationally complete, I can rewrite each of the Pauli operator in terms of the basis of the POVMs. So I'm just decomposing each of them. Then I regroup the terms, and here I introduce a different notation. This is pi m. You see, now this is the generalized measurements over all the qubits, okay? I'm the n qubits. And of course, it's informationally complete as well. And then I regroup all these terms, and I call this coefficient omega m. This is just a coefficient, okay? I'm just regrouping term. And now you would say, okay, what's the advantage here? Initially, you had k terms of the order of, say, n to the fourth. Now you have 4 to the n terms. So is this actually really an advantage? And in order to understand why this is an advantage, we have to notice that if we calculate now the expectation value, because of the properties of the POVM, now this is the sum over m of omega m, where this Pm, you see, is the probability to obtain outcome m. And now, the way in which we can calculate this probability would be very another suspense. Ta-da! It doesn't work, but it will come. This is super important. I know you are all there thinking, how are you calculating this probability? I don't know why this doesn't work. Let me just try again. stuck. Yeah, okay, maybe I use it in this way. It's by means of a Monte Carlo integral. So what you actually do is really calculating really a statistical average of these coefficients omega m classically calculated by over the probability distribution pi m, okay? So just for those of you who are not familiar with Monte Carlo integration, what one does in Monte Carlo integration is to evaluate integrals over high dimensional domains in an efficient way, just by randomly sampling different points within the domain and then averaging over a suitable function. And this is what we do. So to make it clear, what we do not do, this is not how you do, you don't calculate all the PM as mean values of the pi m with high enough precision, and then you average. Okay, that would be not efficient, 4 to the n terms. You don't want to do this, but instead what you do is you measure S time each local P of M, all of them, and this allows you to sample. So the measurement results are a sample, okay, of really, and this is on a quantum computer. And then you have, after you do this, but then what you can do is that you can calculate these coefficients, because now you have sampled this MS, right? So you calculate the corresponding coefficients. And this requires only polynomial time on a classical computer. And finally, you calculate the estimate of the mean value just as an average, okay? So notice that this has two parts. This is a quantum part because it exploits measurements on a quantum system. And this is classical. This is all done on a classical computer, and it's efficiently performed. Now, of course, you may think, well, how large is this S? Eventually, how many times do I have to repeat S? And also, ideally, you would like to understand also how S scales with N. As my n-qubit system is larger and larger, what's the scaling? And in order to understand first how large is S, I will show the scaling later on. We notice just that this estimate converges to the exact mean value with an error which is given by the variance of this probability distribution, the square root of the variance divided by S, right? So actually what it turns out really is a consequence of Monte Carlo integration, and for almost all Hamiltonians, unless some pathological cases, this S is really way lower than 4 to the n. And also what is interesting is that you are estimating the average of the Pauli strings simultaneously, all at the same time. So this is the total statistical error. And this is way better, of course, because also in this way, you naturally take into account the covariance between all different measurements. Otherwise, would be a problem in the calculation of the Pauli strings. Now, how do we use this for an adaptive measurement protocol? Okay, so we introduced the Monte Carlo template. What else can we do? Well, it's important to notice that, of course, the choice of the measurement that we perform given a certain observable may be more or less optimal, okay? Depending on the type of observable, you can have better types of measurements to extract this information. In general, modifying the P of M results in a different probability distribution, PM, and therefore in different weights, and therefore in different variances in the estimate of the Monte Carlo integral. So, however, the nice thing is that you can use just classical post-processing to navigate into the space of all the possible generalized measurement towards the one that is optimal, that minimizes the variance for your observable, okay? And the way in which you do this is because since the measurement you do are informationally complete, you can use the same data that you use to estimate the mean value of the observable to calculate the variance of other measurements that you have not yet implemented, okay? But you have the way of estimating, because you are using informationally complete data. You can estimate anything in principle. So you estimate this variance, and then you use a gradient descent optimization method to choose which other measurement has the lowest variance. And so therefore you implement in the second step a new measurement which is better for the estimate of the given observable. So this is an adaptive strategy which allows to change on the fly the measurement you perform in order to minimize the total error. Now, how does this work? These are some results. I will try to explain. Let's start with the first one. This is the problem of estimating the ground state energy of a given molecule. In this case is H2, implemented with a certain number of, with a certain basis set, which leads to 8 spin orbitals, and therefore implemented with 8 qubits. Okay, so this is what I plot here is the error in the estimation of the ground state energy as a function of the number of shots. Okay, obviously, as the number of shots increase, the error should decrease because I'm performing a better estimate, and then comparing different methods. The direct observation of the Pauli operators, the grouped Pauli method, and then our approach without optimization, and the red case is our approach with optimization. So what you see here is that all the other methods have a typical 1 over square root of S scaling, just you increase the number of shots and decrease the error. But here you start with a certain value, say with 1,000 shots, a certain value of the error. But then you use the adaptive strategy to change the P of M. Because you are changing the P of M towards a better one, the error is decreased. Okay, you're using a new P of M. Then again, you use a new P of M, your new P of M, and you see how the error decreases way faster, of course, of 1 over square root of S. So the adaptive method is effectively working, and eventually it overtakes all the, for large number of measurements shots, it overtakes the existing methods. And you see that actually, well, there is an intuition already here that if we increase the number of qubits, when the system becomes larger and larger, the adaptive strategy works better. So you cross the other methods before. In a way. Okay. This is a movie in which I show how this adaptive strategy works, how this you can navigate, how the P of M changes as I proceed with the optimization. And what I show here is a way of visualizing the generalized measurements geometrically in something which is similar to a Bloch ball. So there is a way of geometrically visualizing each single qubit P of M, representing it in this way. This is not exactly a Bloch ball because, well, it's not unit. So as you see, the parameterization is different. But you will see here the planes, XY, XZ, YZ. So these are the different planes of this generalized Bloch ball. And then you will see different colors for different qubits and different symbols for different P of M's, because the optimal P of M's will change also depending on which qubit, on the different qubits. And this is actually how it works. They start from these black dots here, black symbols. These are the initial 4 P of M's. And then they start moving and converging. Of course, these are very many realizations, converging towards different P of M's, and with a certain consistency, of course, for each qubit, okay, after many, many repetitions. Now the next question is, how does this scale with n? So how is the improvement in the number of shots needed as the number of qubits improves? So how efficient does this work? And here we have, again, a comparison between different strategies, different techniques. And the one that we use, in which we use the generalized measurement and the optimization strategy, is the red one, okay? So what do I plot here? First of all, the system is a hydrogen chain. If I want to study scaling, I want to increase the number of qubits, right? So I add one atom at a time in the chain, and this corresponds in the after qubit to Fermi to qubit mapping to increasing the number of qubits, 4, 6, 8, 10, 12, 14. And what I want to plot here is the number of shots, of repetitions, needed to reach a certain accuracy, okay? An accuracy which is useful, for example, for quantum chemistry calculations. And this is how they scale. And actually, it was already known that the scaling for other methods, well, for all the methods known is of course, follows this law. So what is interesting here is the exponent of n. And you see in this table different exponents for different methods. As a matter of fact, this is something I have not been talking about because this is a quantum chemistry Hamiltonian. The method, all the methods really are depend on the specific type of fermion to qubit mapping that you apply, and because well, I can describe it later if you want. But in any case, there are always type of fermion to qubit mapping such that with the gradient descent method, the exponent is around 3, our exponent, while the others, as you can see, are way higher. So there's a significant reduction in the number of measurement shots needed with this approach. And in fact, our approach is comparable, really, this scaling is comparable to the best known, in this recent reference is the best known scaling for quantum chemistry Hamiltonian obtained by the Google team, which is actually close to 3 as well, so it's comparable to that result. Except that in their case, really, it is specifically for chemistry Hamiltonian, and it includes, a certain amount of extra gates, so it increases the circuit gap. So first take-home message: this hybrid quantum classical Monte Carlo sampling allows to combine an adaptive strategy, which leads to avoid actually quantum state tomography and reduces the number of measurement shots, which is something that is a very sensitive problem at the moment in quantum simulations. The second, so actually, in a way, if you want, the message behind this is really like, okay, maybe we should forget about the density matrix when we measure, or the reconstruction of the density matrix. It contains way too much information with respect to what you actually often needed in the experiments. And so it makes sense to think just purely in terms of statistics and what is the best statistical approach to extract information when you perform a measurement, since quantum mechanics is a statistical theory. And finally, last piece of result, evaluation of different quantities from the same measurement set. And yeah, I make an experiment. So I look again at this specific example of 8 qubit implementation of hydrogen. And I use the same data set to calculate the energy here, the red and the green, with the informationally complete POVM, to calculate something else. And in particular, what we calculate with the same data set is some sort of tomography. In this case, the reduced state tomography. So this is we reconstruct the K-body reduced density operator. So we trace away all the rest. In this case, we have 8 qubits. So we reconstruct the 2, 3, 4, and 5 qubit reduced state. And we see what we calculate is the infidelity, 1 minus the fidelity. And here the fidelity is just with respect to the exact density operator, so defined in this way, the tomographic with respect to the exact. And you see that the infidelity is, in any case, in the worst case of the order of 10 to minus 2 for the non-adaptive case, while for the adaptive, adaptive strategy, it is definitely lower. And so you are actually able, in a way, to also reconstruct reduced state tomography using a number of efficient algorithms that have been recently introduced, and I will not discuss this. So this is the second take. The second message: because of informationally complete properties of the generalized measurement used, we can use the same measurement dataset to estimate other properties of the many-body quantum system. And here I'm close to the summary. Actually, not close, I am at the summary. I'm telling you the summary. Okay, it's great because it's the summary, people think, okay, it's over. No, I will have also a few more words, but yes, this is the summary. So what I presented to you is an algorithm for the efficient estimation of the mean value of observables, which exploits informationally complete generalized quantum measurement and incorporates 3 different pieces. The first one is a transformation of the measurement strategy into a Monte Carlo sampling problem. The second one is the idea that we can actually, on the go, optimize the measurement in order to find always the one that is minimizes the variance. And finally, I have not actually described this, but I want to mention this. Actually, this happens without additional measurement overhead. So actually, we have a way to combine, this is just post-processing, classical post-processing. We have a way to combine all these different estimations of the observable on the go, so as we navigate in the space of measurements. And of course, this method does not require exponential resources, neither in the classical nor in the quantum parts. Okay, so it is efficient in this sense. So what are the advantages of the technique? The first one is, I mentioned it several times, the example I showed is an example of quantum chemistry, but actually the whole method is completely agnostic on the nature of the Hamiltonian. And it is inspired, of course, by some quantum chemists. It is inspired by actually concepts of quantum information, like the one of generalized measurement, and applied to certain quantum simulation problems. Also, the method is exact. Okay, we have not done any approximation, except, of course, the fact of having a statistical estimate of the thing, but it is exact. And importantly, from what I showed you and from our analysis, it suggests that the adaptive strategies leads to a very good scaling. Okay, obviously, this is something that we are still further exploring, because there are many ways of optimizing further this method. So what are our future directions? Well, first of all, we would like to apply this technique to other problems, maybe other than molecular Hamiltonian cases, maybe some condensed matter cases, or other technique. The second is that improvements in the parametrization of the P of M. I didn't show at all what is the parametrization of the unitary that we use for the P of M, but they can be certainly optimized, as well as the gradient descent-based method can be optimized further. And finally, of course, we can also use or think of using classical machine learning methods accompanying these techniques, in particular to enhance the measurement adaptation step. Another thing is, in the context of VQE, and for those of you who are more familiar with VQE, actually we have not integrated this method fully in the optimization of the VQE ansatz, and this might likely lead to further increase in the whole VQE optimization procedure. And I think this is everything I wanted to tell you. I thank you very much for listening, and I'm very happy to receive questions.
Thank you very much, Sabrina, for this very interesting talk. I have seen already 2 questions online. Maybe we start online and then we come to Maciek. There was one very early. Okay, so Michal Osmaniec, I would like to ask a question if possible. Yes,
it's possible.
Can you unmute yourself and ask the question?
Sure, can you hear me? Hello?
Yes.
Yes, we hear you.
Thank you for the great talk. I wanted to ask like a technical question. How does your method compare to those techniques by Preskill, Kang, classical shadows? So
yes.
Do I understand well that they're sometimes use local Pauli measurements while you do locally some information like complete P of M's. Is that correct?
Yes, it's a very good question, and we are working on comparison with classical shadows methods. The first thing is, it's funny because I don't know where to look, because it's not here. Hi, I don't know if you see me, but it's there. Hi, sorry. Okay, so there are some points which for sure we know are different. The first one is that, of course, the classical shadow approach does not include any adaptive or iterative method. So the whole part that we propose, in which we use the informational completeness in order to optimize the measurement adaptively, is different compared to the classical shadows, and is new. Then, of course, also classical shadow methods use, in a way, informationally complete P of M's, but the way in which they do this is really by using, by randomly sampling this unitary that it is implemented. While in this case, this is different because as we need to navigate the space of POVM, okay, I'm telling you something that I mean, we are working on, we are studying. I think that it seems to us that actually the lack of restriction in our parameterization of the unitary, which implements the POVM, the lack of any restriction to this random sampling allow to navigate the space more, let's say, fully in order to find the optimal POVM. But of course there are, and then the third thing that I can say is that for classical shadow tomography, as far as I know, I've seen only one paper in which they implemented on chemistry Hamiltonian, and the scaling is very bad. So in itself, unless, I know that, because I was talking recently with one of the authors of the shadow tomography paper, and I know that they have an optimized version of the shadow tomography. There have been many actually papers following up, and maybe this might be something that can be also considered. But for the existing results of shadow tomography on chemistry Hamiltonian, the scaling is way worse compared to ours. Actually, also compared to the Pauli methods.
Thank you. The next question is Maciek, please.
So I was wondering, I mean, in statistical physics, so about first part, so to say, of the whole procedure. In statistical physics, very often Monte Carlo sampling is formulated as stochastic process in which I go from one configuration to another with the rates which assure that I sample from the right probability distribution. Now, of course, there are many ways of choosing these rates and optimizing them. I don't know, the simplest example, kinetic Ising model. I can take single spin flips or 17 spin flips, and in different situations, they are better. So there must be some place for this kind of optimization in your approach, especially in the context that in the recent years, there is a huge industry of improving Monte Carlo sampling related to all this use of graphical cards and things like that, which are much faster computers of special purpose.
That's a very good point. So yes, there are, and we have not been using any advanced method, okay, that, as you say, it exists for optimizing the Monte Carlo sampling. It would be very nice to do it. At the moment, really, our main point was to shift really the perspective on the measurement to say, well, you know what, we can use Monte Carlo sampling, but you are absolutely right. In fact, there exist a lot of techniques that should be and can be used, and they can lead to scaling. This is like this scaling is really the worst case scenario. You can really have way better scalings. And yes, it's true.
Thank you. Yes, can you prepare the microphone there while you take the next online question? So Christian Kinakerhard. As far as I understand, your measurements are destructive. How does this compare to methods in which the system is continuously measured in a non-destructive way?
The answer is, I don't know. We have not done a comparison with the continuous measurements techniques. I do not. I really don't know. I mean, actually, if there is anyone in the audience who knows or who has an idea of, just they are not, as far as I know, for the chemistry Hamiltonians, they've not been used, and so I don't have, or at least in the later literature, I have been considering. They mostly use measurements of, as I mentioned there, of these Pauli strings, just direct measurements, accumulate statistics. I guess that what is, no, this is absolutely no dynamics. Okay, probably if I don't know, actually, I don't know. Maybe you can have continuous measurements just to improve the precision. I don't know, but.
Okay, yes. Let's take the next question here.
Hello. So you asked for an experimental perspective.
Yes.
And what is my thought is that your scheme requires adaptive measurements, so it requires feedback. And this,
sorry?
The scheme you propose requires feedback, I suppose, because it's an adaptive scheme. So this experimentally costs time because you need to finish the previous measurement before you set your apparatus for the next acquisition. if you consider experimental time as a real resource, how would things scale? Have you looked into?
Yeah, that is a very good. It's a very good point. And no, we have not been looking at that. Of course, I could say so. The one point that I did not go into detail here is the fact that the optimization is done on the fly. So we use all the shots at all times for each step. What you would need to do is actually change the parameter of the unitary. So the implementation, let me just see. So while I do not have an answer, but I'm just trying to tell you specifically where this could come into place. And obviously, I also have to say that this will depend.
That plot there that you have for different methods. For actually, I have 2 hours on the machine, and what can I do best?
So the thing is, it will depend definitely on the specific implementation or measurement settings. What we will have to do is to change this unitary. It's just a rotation, okay? It's a 2-qubit rotation. So you have to change this parameter towards the new one. So and then reperform the measurement. So I do not know for sure. This might require some additional time. With respect to using always the same, but I guess that this will depend on the specific experimental setup. I assume that in general, for certain, for example, well, I don't want to.
No, but that's the point I'm making, because for full state tomography, you also need to change the unitary. Yes, to do the different projective measurements.
I mean,
the fact that we have to finish acquiring the previous data before you set the next one in an adaptive scheme. That this is typically much more time costly than when you know a sequence that you need to set. Anyway, thank you.
Okay.
Okay, thank you. We come to the last question online. Pedro Maniani, good morning, professor. Great talk. Question: when showing the 8, 12, and 14 qubit graphs, the 12 qubit showed a steeper slope when compared to the other 2. Why is that? Does it mean you have a better number of qubits to apply the method?
You mean, okay, this is the one, and the 12 qubit. No, honestly, I don't think, we cannot infer anything from the fact, or we don't have an explanation from the fact that it does seem to have a steeper slope. I mean, all these optimization techniques do depend, of course, on the specific implementation of the observables, and also on the specific, they also depend, by the way, on the, so there is a change depending on the type of initial POVM that you choose. You can choose, so you can even think of optimizing the initial measurement beforehand, classically, and then of course the scaling would be, the wall behavior will be, the adaptive strategy will be better. But no, I don't think that there is specifically a reason that, you know, or something that we can identify in why this seems to, this adaptive strategy here works better.
Okay, so are there more questions? If not, we are perfectly on time. Let's thank Sabrina again.
Thank you.